but there's no guarantee that it'll even work. Okay. In theory, we're live. People need to say hello.
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 Hey.
Well, I say everybody's names. Anybody who wants me to say hello to them, they have to say hi in the chat, and then I'll say hello to you. So, yeah. So apparently there's a really close conjunction of a bunch of the planets right now, like Saturn, Jupiter, in the morning sky are really close together.
Mm-hmm.
Not as close
How
as...
early in the morning do you have to...
Yeah, I mean, it means waking up or staying up, right? But nowhere near as close as what we're going to see by the end of the year when you'll be able to see both Jupiter and Saturn in the same telescope field of view. They will be like that far apart. I believe, that many arc seconds. An arc minute? A couple arc minutes? Anyway, they'll be close. All right. Here we go, people. Hello to Adam Synergy, Andrew Planet, Andy Cowley, Bob Moeller, Brad Hogue, Brexit Denier, David Fairweather, Frank Tippin, Horizon Brave, Ian Farquharan, John Musk, John Wells, Johnny J, Kevin Ayers, Kira H, Larry Beckham, Luke Duke, Miss Scooper, Nancy Graziano, Paranor, Peter Hoole, Rich Wilson, Sergio Botero, Susie Murph, Troy G, Uncle Bill Druin, and Var. Welcome, all. Ian Farquharan's experience, childhood, was my exact childhood, too. Living on a hippie commune island off the coast of Canada. Talking about the prevalence of various medicinal substances in their local community. That's Canada, West Coast. Anyway. How's everybody's quarantine going? Anyone?
It's
Making it through.
Yeah, I mean, my sleep schedule is shot, and I don't know what day it is until someone tells me, and my cats are driving me nuts. But other than that, I'm good.
Yeah, they're a little sick of you, right?
I'm a little sick of them, honestly.
Yeah, they're like, wait a minute, we didn't sign up for this. We would have, like, most of the time the place to ourselves, not have a human being all up in our jam. But apparently that's out the window. Yeah, our dog is just delighted. Right?
It was my favorite headline was dogs absolutely loving whatever the heck is going on.
Yeah, exactly. Like, oh, I just get to hang out with you all day long, 24/7. Yeah, the pack is together.
See, I think my cats are loving it. They're all over me. Like it's just a constant play with me, pet me, love me, snuggle with me, and it's like I have things to do. Get off my keyboard.
Yeah.
You try studying like the fake keyboard or the decoy keyboard next to your real one. They go to that one.
I should.
Oh, that's a great idea.
I mean, this is a laser pointer right now, and I'm trying to keep one distracted because she sits here and sticks her claws in my knee while I talk.
Oh, I see. So you're like during the show, you are. I
am, yeah.
Leading a cat around your living room to keep her out of your out of the camera.
Yep.
That's quite
if I don't, she will get up here and she will sit next to me and stare at me. So
yeah, it's possible I've had to host a show while also keeping a dog from losing its mind while my wife was outside of the house. It's possible this happened where I'm like petting the dog and trying to just keep it from not yelling.
At least the lazy one isn't very noticeable. He's very tucked in behind me, so you can't see him.
All right, let's put you all back in your boxes, and we will begin this show. All right, here's me. Here's my introduction. Here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, April 15th, 2020. Our quarantine continues. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about black holes, folding light back on themselves, and maybe the universe isn't isotropic. Scientists discover an Earth-sized planet in Kepler data, and the 100th lunar asteroid collision confirmed by telescope. Joining me this week on my screen right now, I've got Beth Johnson. Beth, welcome back.
Hi.
Is it possible you were supposed to be here last week?
Yes, unfortunately, last week the insomnia monster
Yeah.
brutalized me a lot.
Yeah.
And I would lay down for what I would think would be a 90-minute nap, and I would wake up 5 hours later.
I have been waking up every night at like 3 a.m. So I've been trying to go to bed. Like I've been trying to exercise. I've been trying to go to bed at a normal time, and I'm waking up at 3 o'clock in the morning. And then if I'm a bad person, I read Twitter for like an hour, just like, oh yeah, the world's falling apart still. And if I'm a good person, then I just lay there and I try to get back to sleep. And then I wake up again around 6:45 and then I'm on with my day. But I think there are no rules now for sleep. So we got Michael Roderick. Michael, welcome back.
Hello.
And you got your new Twitch streaming set up now, so...
Noise canceling, so if my dog does go crazy, I won't be able to hear him, although you may.
Right, so we'll tell you.
Let me know.
Michael, the dog's freaking out. Yeah, all right, we'll let you know. And we've got Dr. Brian Coberline. Brian.
Hi, everybody. It's good to be back again.
Thanks to have you. All right, so before we get into this week's special guest, I want you to take a second and give a huge thank you, as usual, as always, to our good friends at the Weekly Space Hangout crew. If you're listening to the show as a podcast and you're like wondering how you can get a direct line to astronomers and astronauts and anyone in the space community, join the Weekly Space Hangout crew. Then they'll make you a executive producer of the show. Then you've got all the clout that you need to be able to reach out to any astronomer, astronaut, anyone in the space community and bring them on as a guest of our show. So it's great. And they're a great community, great people to talk to. So really rewarding. And we couldn't do the show without them. So if you haven't already, go to wshcrew.space and they will hook you up and put you to work. All right, let's get on to this week's guest. This week we've got Laura Forczyk. Laura, welcome to the Weekly Space Hangout.
Thanks for having me on.
So who are you? What do you do?
Oh, my background is in astronomy, astrophysics, and planetary science, and I just wrote my first book.
Nice work.
But aside from that, I own my own company. It's called Astralytical, and we do space consulting for space science, space industry, and space policy. And thankfully, it's a bit of everything because I'm a generalist. I absolutely love everything space.
So what did you specialize in when you got your degree?
For my master's, it was gamma ray bursts. And then I switched over to what I call experimental planetary science, where I did a lot of work in the lab with Regulus simulants for lunar, Martian, and any kind of planetary surface that has dust. And trying to figure out the dust dynamics and planetesimals and really got me into industry because we realized, hey, we're going back, and I'm absolutely a moon geek. Everything about the moon.
I am likewise and have been sort of compulsively interviewing moon specialists for some of my videos.
I've worked with Phil Metzger and Ryan Watkins.
Phil Metzger and Ryan Watkins. Yeah, exactly. And I just am. I suspect like I find that whenever anyone thinks that something is easy, I suspect that it's a lot more difficult. And then when you talk to someone like Phil Metzger or Ryan Watkins, you're like, okay, yeah, no, it is an enormously complicated adventure to try and settle a place like the moon, even try to extract any resources. Like, we don't know really yet what we're in for, but that's sort of the point, right? The adventure.
Yeah, you can't really know until you go ahead and try. And that's what they did in the 60s and 70s. And now that technology's improved, maybe we can get the politics to fund it so that we can actually get back there.
So what's the book?
Rise of the Space Age Millennials. So I never saw myself as an author, but about almost 4 years ago now, I realized that there were all these stereotypes coming out about millennials. And if you don't know, millennials are in their 20s and 30s. So we're not talking about kids here, although some people I interviewed were undergraduate students, all the way up through CEOs of their own company. I interviewed over 100 people because I wanted to get a better perspective of who these millennials were. And I stuck to my wheelhouse. I stuck to space because that's what I know. I didn't want to do a wide variety of millennials because I myself wanted to probe, what are millennials in space, either working in space or studying to work in space? What do they think? What do they feel? How do they, think about what it is that we're doing in space and where we should be going?
I mean, I will admit that I kind of bristle at just the term itself, because it is it's just like a thing that every generation does, is to bemoan the work attitude and ethics of the coming generation. And that whole kind of boomer joke, right, goes on. And yet I find that, anytime you try to paint any generation with a broad brushstroke, it's a waste of time. So did you find that stereotypes were reinforced or broken apart?
For the most part, broken apart, but there were some that were definitely reinforced. So as you said, it's hard to paint with a broad brush. Everybody is different, and I got a lot of different perspectives. With 100 people I interviewed, lots of different perspectives. But there were some commonalities. For example, how we were raised with the connectivity. So we were all raised with the internet. Smartphones came in there as we were coming of age, or younger millennials when they were young kids. And that really raised our ability to be connected at all times. Also raised our ability to see the world internationally. So whereas older generations, the big dawn of the space age was all about, Soviet Union versus the United States and America first, you still hear that terminology. That doesn't ring true for millennials who grew up in an age where everything is international. We talk, on social media, and we don't know who we're talking with and where they are. And international partnerships and collaborations are much more the norm now. So those are the kind of commonalities I saw just based on the world that we grew up in. Yeah. So there are some stereotypes about, impatience and entitlement that didn't necessarily hold true. But there were definitely some about, addicted to smartphones and social media that in some cases did.
That's only the younger generation. That is definitely not something that is impacted the rest of us at all. I've been doing this job for about 20 years now. And I have really experienced, early on, I would say that, if I was to sort of gauge my audience, there was obviously enthusiasm for space, because they were self-selected to be, they were hanging onto a thread from the original Apollo missions through the space shuttle and to whatever came next. But there was definitely a lot of sort of sadness and ennui for the fact that we hadn't gone back to the moon. But in the last 10 years, thanks to a certain plucky startup led by Elon Musk, you really felt this resurgence in excitement and enthusiasm for where space is heading. Many new interesting companies are happening, and it really feels like people think it's going to happen this time. What's your sense of sort of the overall, back to, let's put them all in a box again. How do millennials feel about space exploration?
Yeah, there's definitely some cynicism, as you alluded to, but for the most part, people are really excited and passionate about the new space age, new space, quote unquote. And it's funny because last year is when I wrote the majority of the book, and that was all about Apollo, looking back to Apollo. And even now we just had the 50th anniversary of Apollo 13. Mm-hmm. It's ongoing. And so it was very retrospective and nostalgic for the older generations, but not necessarily for millennials, since they didn't live through the Apollo era. They never saw that. So millennials got inspired by what's in front of them. For older millennials, it was a lot of the NASA Space Shuttle, International Space Station, and some of the really cool probes that we've sent out to, Saturn and Jupiter and Pluto. But for the most part, the number one reference that got millennials excited is SpaceX and the new space movement. SpaceX, Virgin Galactic, Bigelow Aerospace, and some of the others, along with some of the accessibility aspect. So CubeSats and small sats being more accessible so that people can really themselves personally touch something that is space hardware and launch something to space, as well as the idea of space tourism, which we still haven't quite seen happen. We've had a few go to the International Space Station in the 2000s, but the idea of they themselves and everybody who wants to go can go to space, that kind of inspiration that's just right there to touch, that's really inspiring.
So are you finding, you know, a thing that I see as well quite a bit is like people have entered some kind of career, like they've gone into computer science, or they've gone into engineering, or they've gone into education or something, but because of all this excitement that's happening, they've gotten really enthusiastic about space and they want to play a part in it. So for people who are already established, like if you're just going to university, it's obvious, right? Just keep going to university, become an engineer, computer science, or, you know, physicist or astronomer, whatever, and just keep going. But if you are already established, but you are sort of in this cohort, what can people do to get involved?
Yeah. So within the book, I highlighted the idea that millennials are really inclusive. And that's inclusivity in terms of, you know, race, gender, socioeconomic background, geographic location, but also inclusivity in terms of the types of people that we send up, the backgrounds, the industries, the expertise. People want normal people, not just, you know, the people that we sent, the right stuff of the Apollo and Gemini and you know, the Mercury era, but everybody. And so I actually do a little bit of space career coaching to help guide people into paths. And the majority of the people I speak with are mid-level professionals who are not in space, who want to go work in space.
Yep.
And the beautiful thing is that it is so accessible and multidisciplinary, interdisciplinary, and really any discipline, any industry, any background can go in space. And I try to guide people as to how they do it. And yourselves as a journalist, educator, communicator, those kinds of things are somewhat obvious to us, but may not be obvious to others. And then you've got other people who have these fantastic skill sets and they just don't know how to apply them to space. And I really help guide them through it.
Yeah, it's funny because space, I mean, absolutely, it is rockets. You know, there are a certain amount of the engineering and scientific components to it, but at the end of the day, it's transportation, it's research, it's communication, it's all of these things. And so if you have a certain skill set, it's a matter of tuning up your skills to be more focused on that, into that field. And there are a mountain of opportunities and more of them opening up every day. I mean, when we just look at, say, what Starlink is doing with SpaceX, I mean, that's potentially a multi-trillion-dollar industry that they're going to be going into, that's going to help fund the development of all this new research and excitement. So what are some other parts of the book that you're quite sort of excited about and got a chance to communicate?
Yeah, kind of what we touched on with what they want to go into. So what millennials think should be the next 50 years. And it's a lot of what we just touched upon, you know, the space tourism and the access and democratization of space, the broadening of space, but it's also things like going back to the moon. For the majority of people, it was going back to the moon and onto Mars. For some people, it was just go straight to Mars. But in either case, millennials want to and hope to and expect to see humans on Mars. That's like the kind of goal right there. It's not maybe the ultimate goal of space. A lot of them want to go into deep space, go to, you know, Europa and some of the really cool places where we could find life, either life in our solar system or life on exoplanets was another one that millennials really want to go after. They want to find that biosignature that tells us whether or not we're alone in the universe. And some people really like the idea of, you know, these multi-generational starships is getting a little bit more into the future, probably not in the millennial lifetime, but that was something that really inspired millennials to go work towards.
So for a person who maybe isn't already partway through their career, but actually is in that earlier stage, just going to either university for the first time, or maybe they want to go back and get some new skills, where do you see like the biggest demand?
Oh, that's hard to say. I mean, if you go look at job descriptions, job postings, it's all still engineering.
Yes.
And it's gotten to be more of like a broader engineering, I think, systems engineering. But some places still very much like the specified aerospace engineering or mechanical or electrical, or computer, whatever it is. I myself am a scientist, so it's hard to go wrong with physics that can be applied broadly anywhere, really. I'd say, you know, just go after whatever field is truly interested to you. If you love art, go after art, because space art is everywhere. I mean, I see it in the background of yours, the background of mine. Art is everywhere. I mean, like whatever field it is that you're passionate about, you can apply it to space. And I've had, I speak to student groups sometimes, and I've had them quiz me, you know, what area do you want to go into? And then I tell them how to tie it to space if they want to. Really, it's anything. So people could always reach out to me if they really aren't sure and they want to get involved.
I mean, people always ask me, like, I want to be an astronomer. What should I do? And astronomy is great, but there aren't a lot of jobs. And maybe that's something that you experienced. There's a lot of people who want the jobs, and there aren't a lot of permanent positions. But if you also take, say, computer science at the same time, then there's a million jobs, too many jobs. And so if, that whole astronomer idea doesn't pan out, you can always, work for a couple of $100,000 for a tech startup instead. So
science is a big one right now and growing.
Yeah. And in fact, really, at the end of the day, now these days, astronomy is computer science. Like, the same skills required to develop on a search engine are the same skills required to help search for asteroids in a gigantic database. So I always highly recommend people, just whatever you're doing, also learn computer science, because at the end of the day, it's not super complicated, and is a wonderful addition to literally any kind of work that people are going to want to do. So
I'm going to push back on you a little bit.
Yeah.
I think that's great advice for a lot of people. I myself absolutely hate computer programming,
Yeah.
which got me away from astrophysics and more towards planetary science and more towards the hands-on work.
Sure.
So I think it's really where it is that you find that passion, that spark,
Mhm.
not because someone else told you, but if you were doing something for free because you were independently wealthy, what would that be? Is that computer science? Great, go ahead and do that. But if it's not, don't feel pressured, because you can find your own path.
So there was a question here that I liked from Arjone. Will the millennials be the generation that creates space industry and normalizes space travel, or will they make the infrastructure for the next generation?
Oh, I'd say that space industry is already here, and it depends on what your definition of normalize is. Are you talking about like buying a ticket to space, like you buy a ticket on an airline? That's maybe not millennial generation, although I hope so, because I'd like to go buy a ticket to my kids or my grandkids someday.
Yeah.
But I don't know. No one can really predict these kinds of things and how it's going to go. We know that satellites are going to increase. So that's pretty much guaranteed. We're already seeing that in real time, just how many satellites and how many launches are going to be required for those satellites. Whether or not those mega constellations planned right now are going to succeed or not, I don't know.
Yeah.
But when it comes to human spaceflight, it's so hard to predict how far we're going to go and how quickly. I can probably say with real assertion that we will go back to the moon in my lifetime. Whether we go back by 2024, probably not.
Yeah.
But I'm really hoping in the next decade, but you really can't know because these things are so uncertain.
What is something, though? I mean, I think that the aspirational, inspirational thoughts about exploring space is partially influenced by, I think, the science fiction that we all have grown up on. And space is a lot worse than Star Trek has led us to believe. What is the sort of the cold reality that you maybe hope more people understand as well?
Oh, I think we already experienced enough cold, hard realities.
Yeah.
I mean, Mars has been the goal since we landed on the moon, since 1969. That's how long Mars has been a goal, and we're still not there. So that's enough cold, hard reality for me.
Yeah.
I'm quite happy continuing to try to get to that path.
Yeah.
I myself, a moon geek, I think we should go to the moon first and learn as much as we can and have a permanent international habitation. The moon's village concept, the Artemis Phase 2 concept.
Yeah.
Whether we get there, I don't know. Because it, like we said, it is tough and there are these complications, but we can do it because we've got human ingenuity. We've got the will. Hopefully we have the financial and political will, but we at least have that kind of imagination, that kind of like, we can do this kind of mentality where eventually we will be able to.
So place your bets. When does a human set foot on Mars?
Oh gosh, within my lifetime. I don't know how long I'm going to live.
I'm going to need a number.
I don't place that far.
Fine.
I'm an analyst. I don't go that far.
Okay. All right. Understood. All right. Well, Laura, where can people find out more?
Great. You can go to my website, which is astralytical.com. There's a link right there if you want to buy the book. It's on Amazon, paperback, and ebook. It's also on Barnes & Noble ebook. And you can get an autographed copy on my website. You can also find me on LinkedIn and Twitter. Congratulations on writing a book. Now you decide whether you're going to do the second one. That's the... Oh, I am. Good. I am. That's when you're serious. I know. That's impressive. I've got the bug. Yeah. Many people only write one book. So good on you. Well, thanks, Laura, for coming on the show, and good luck, and to all your millennial friends. Thanks so much.
All right, take care. All right, let's move on to the news this week. Brian, I want to talk about black holes folding light back upon themselves. What?
Okay, so we think of a black hole as defined by its event horizon, which we generally know that that's the point that if you get too close to a black hole, not even light can escape. That's where you're doomed. But the interesting thing is that even if you're not at the event horizon, light is still affected by the gravity of the black hole. It's not that if it stays away from the event horizon, it's free and clear, because gravity can deflect the path of light. It can cause its path to bend. And so light can go in orbit around a black hole.
Yeah.
If it's close enough. But it can also follow weird paths. So that's...
I'm sort of imagining like how comets will go around the sun on this weird elliptical path.
Yes. So they would typically more go in parabolic paths, but basically the idea is right. The other thing is that the rotation of a black hole also twists the space around it. It's called frame dragging. And that means a beam of light can actually cause itself to change direction as space is twisting around it.
Right.
So we've known about this for a long time. And, if you see movies like Interstellar, you see these kinds of warped light effects, but it's hard to observe in real life. So this new study looked at light, X-ray light coming from what's known as the accretion disk of matter around a black hole. So you've got your black hole that's spinning, and then around this you have this disk of superheated gas, basically. And it gives off X-rays. Well, a lot of the X-rays, when they leave the disk, they just go off in a straight line, basically, in our direction. But some of it, if it is close enough, it's in the inner part of the disk, instead of kind of just going off, it actually bends because of the black hole's mass.
Right.
And so what they found was when they looked at these X-rays, some of the X-rays were coming directly off the accretion disk, but some of the X-rays were actually scattered. Their spectrum was different. So they were X-rays that were scattered off of the accretion disk. And the only way you can do that, since the accretion disk is the only thing that's making X-rays, is for light to come off of the accretion disk, get bent by the black hole, and then smack into the accretion disk on the other side. And then it scatters off, and that's when we see it. So we're actually seeing light that's being bent around the black hole, and in some cases being bent and twisted around the black hole and then scattering off.
Right. I mean, literally
all of this light dance is happening.
Like most of the light is not even making it out of the black hole. The light that is escaping from just around the black hole, most of it is going into the black hole, but some of it is getting out, and even that is still being curved and cranked back by the gravity, plus with the frame dragging, that it's then smacking into the accretion disk, and then some of that light is getting gobbled back up into the black hole. Like it's a rough, even light.
But yeah, I
mean,
if you were in this accretion disk, you would actually see kind of reflections from the black hole of the other side of the accretion disk that's distorted from the rotation. And so they're actually heating each other up. So you get this, you're getting the scattering effect, which could be part of the reason why you're getting these hot spots within accretion disks.
So one side of the illumination coming from the accretion disk, the light, is flowing away from the accretion disk, getting sucked back down into the accretion disk, and then heating up a chunk of the accretion disk, causing it to radiate additional radiation.
Exactly.
That's madness. That's crazy. Like if we didn't
that's
think
got to be an Interstellar 2.
That's Interstellar 2 is like, oh yeah, we is seeing a black hole with an actual actively feeding accretion disk around it. Like,
yeah,
Kip Thorne's gonna have to come back and do a whole new set of calculations just for that.
Right. Exactly.
Oh, that's awesome. That's awesome. Beth, what do you got for us?
Okay, so Kepler is the gift that keeps on giving. Scientists announced today, NASA and Seti Institute both announced that they have a team and they've discovered a planet called Kepler 1649c. So it's the second planet in this system that is close to the size of Earth. It's 1.06 times the size of Earth, and it's in the habitable zone, so it can have liquid water. So this is kind of a big deal. The reason it's important is that there are exoplanets that we found that are closer to Earth in size, and then we found exoplanets that might be closer in temperature to Earth, but neither had the combination. So this is the first that actually has both of those.
Wow. So I mean, Kepler. I mean, we said goodbye to Kepler a couple of years ago now, and a lot of the data. So how long had they had this data in the system?
Well, so what they're doing is they're going back through what they call false positives. They had an automatic system that was set up to kind of go through all the data and say, this is a planet, this is not a planet. And they had false positives that they said that the system kicked out and said, this looked like it was something, but it's not, and we're going to discount it. So they've been going back through the false positives, and when they're like taking a look at them by hand and by eye instead of just by algorithm, and they said, wait, no, this looks like an actual planet, hold on, let's take a second look. And then that's where they found it in the data. So they're actually doing like just kind of a second pass through stuff that got kicked out.
So how does that work though? I mean, like they are, you've got Kepler, it's staring at this one spot of the sky, it's watching all of these stars, it's seeing dimming, and then they're ruling out things, right? They're ruling out a certain, like the variable stars, and they're ruling out various situations. And then they get these ones, and then they go like, nope, that's not enough for it to be a planet. It could be something else. And so they've got a bunch of these false positives. And so someone had the idea, like, let's just double check these false positives.
Yeah. So Jeff Coughlin, who's actually from the Seti Institute, he's been looking at these signals for a decade, and they just kind of started to go through the automated classifications, and this one basically just kind of got kicked out. So it was detected in the first stage, and then it got kicked out by the automated algorithms in the second stage. And that's when they went, wait, no, let's go back and take a second look.
Right. So let's talk about the planet, because it's pretty exciting.
Yeah. So again, it's 1.06 times the size of Earth. So, it's the star itself is a red dwarf. So that's kind of the big difference. It gets about 75% of the amount of light that we would get. And but still manages to be close in temperature to us. So with those two things in mind, it's potential for liquid water, and that makes it potential for life. And
I mean, at this point, I mean, I don't want to sound like a jaded exoplanet fan, but an Earth-sized world orbiting within the habitable zone of a red dwarf, yawn. But still, I mean, these are exciting, and each one of them is precious. And to rescue one from the false positives bin, I think is pretty great, actually. Do you think, like, in discovering this, is there a rethink about how Kepler data has been analyzed?
I think that it means that the program that they've been working on with all these false positives is, finding a hit means that there might be more. So it's always a good idea to keep going. Automated algorithms don't always work 100% of the time. Yeah. So, having the human in there is always a good idea.
There was a great quote. I don't know if you did the article on the Seti Institute.
But I don't write the press releases, but okay.
Oh, okay. Well, there was a great quote from Coughlin, and he said, this is the most Earth-like planet that has ever been found with Kepler in terms of size and temperature. Mm-hmm. So, like, if you were to stack up all of the planets found by Kepler, this is the best one. Right. And yet here we are, and it was almost thrown out.
So
bathwater.
There are two planets that are closer to Earth in size. One is in the TRAPPIST-1 system. One is sketchy, but it's a Teegarden C. And then there are two that are closer in temperature. One is also in the TRAPPIST system, different planet, and one is a TESS object of interest. And the problem is that, you know, while you have these closer in size and these closer in temperature, the other factors are always off. So in this planet, we've actually managed to acquire both of those factors.
Yeah, and that's key. That's super exciting. And I do hope that, I mean, Kepler, even though Kepler is gone, the data is there and the data is available. And maybe as new techniques come online and people are able, there's more telescope time that's available, they can start to look at some more and more of these signals. I mean, the part that's always kind of incredible to me is even with a fairly small telescope, you can confirm the existence of a planet using the transit technique. I mean, you just need a really good CCD photometer on your telescope, and you're willing to instead of taking pretty pictures of the Orion Nebula, you set your telescope at staring at star Kepler 1649a for several hundred hours. You can confirm planets too, and I think hopefully this will inspire other people to get on board the planet confirmation train. Awesome. That's really exciting. Congrats to everyone at the Seti Institute for pulling this one out of the garbage, which is great.
And NASA as well. That was also NASA Ames. Don't want to leave them out.
Yeah, no, of course. All right, Michael, what have you got for us?
So there's been a project funded by the European Space Agency called NELIOTA, and it stands for NEO, or Near Earth Object Lunar Impacts and Optical Transients. And so the goal of this project is to look for objects that are hitting the moon to try to get an estimate for the kind of surrounding rocky fields that we're traveling through in space. So how much stuff is hitting the Earth? Can we determine that then by looking at the moon? And they just found their 100th object. And it was also confirmed by with another telescope, which is kind of the amazing thing that you get these multiple detections, which really increases your confidence. And so in doing these measurements, you look for these flashes of light on the shaded part of the moon. So you're not looking at the illuminated part. You look for these very brief flashes. So you're taking images about every 30 milliseconds. So very rapid turnaround. And you take it in two filters. So a kind of a green filter and a red filter. And by comparing the brightness in those two filters, you can then work out a temperature for this flash, this impact. And with the temperature, you can get the luminosity of this impact. With the luminosity, you can get the kinetic energy. With the kinetic energy, then you can get the mass. So it's kind of this train of deductions to finally get the mass of these objects that are hitting the moon. And so they've been running for about 2 years now, and they published a paper last year. They found that their Earth is accruing meteorites that are less than about 100 grams at about 100 objects every hour. So there's a lot of stuff that is hitting the Earth.
100 objects every hour.
Yeah.
Are hitting.
These are like small ones, so like 100 grams, so pretty small.
Are hitting us, or hitting the moon.
Yeah. Hitting Earth.
Yeah, hitting Earth.
So in doing this data, you extrapolate to get to see what's hitting Earth.
And I always forget, Brian, you did the calculation, right? Is the Earth getting fatter or skinnier from the impacts versus the atmospheres?
It is. I think it's losing a very little bit of mass at a slow rate because of the atmosphere.
Right. The atmospheric
it's gaining
loss.
Meteoroids, but it's losing because of the atmosphere.
Right. So we're exchanging dirt. We're gaining dirt and we're losing air.
Right. But as we gain dirt, we'll lose air at a slower rate.
Right. And eventually it'll and we'll never stop gaining dirt. So
that's right.
As we gain in mass. It's always funny. People always ask, like, oh no, if we launch too many rockets will eventually remove the mass from the Earth. But the reality is, of course, is more of just of this junk falling down on the Earth than we could ever launch off of this planet. So Michael, it's interesting. I mean, this whole process, I can remember when, I don't even remember exactly when, 10 years ago or so, astronomers weren't even sure this was a thing. This was real, right? They called them lunar transient phenomenon. And some astronomers were like, I saw a flash in my telescope, and other scientists would be like, no, you didn't. And now we're at the point where you've got this incredible, precise monitoring network that is watching the moon and gathering this. So, how sophisticated is this analysis these days?
So this is one telescope that they're talking about. It's a kind of a fascinating system in that it has two separate cameras that image at the exact same time. So it's not like you take an image in one filter, pause, take an image in another filter. You're doing this dual imaging. And so then that gets feeded into a pipeline to look for concurrent flashes. You know, if you had better technology, maybe you could get smaller, finer resolution, and that could help your estimates. But it's still pretty impressive to be able to take an image in order of milliseconds in two filters, compare them that are taken at the same time, and then be able to feed that into this pipeline to look for simultaneous impacts.
And so reading that article, they're able to see these flashes down to, as you mentioned, 100 grams, as small as 5 centimeters.
It's insanely tiny.
Yeah, so
they're looking at like
a rock this big smashing into the moon, 300,000 kilometers away. That's amazing. We can't see a flag on the moon, but if the flag could light on fire, then we could.
When we go back to the moon, we'll send someone to light the flag.
Like the flags on fire, yeah, exactly. And then we'll be able to see them for just a few brief moments. So we
can prove that we did land on the moon.
Yeah, exactly. If you want proof, look at the moon at exactly this time, and we're going to light a couple of flags on fire. What is the what do you use this for? So once you start to know the number of impacts that are happening to the moon, what does this tell you about the solar system?
Well, so kind of the very broad aspect you could say is that we're looking for planetary defense measures. So you want to know, is the Earth in danger of being hit by any kind of asteroids or small rocks? And this kind of gives you a handle on what the Earth is experiencing.
Yeah, I mean, don't forget the time we just mentioned that there's about 100 tons of debris smashing into the Earth every day. So,
Right.
Yes, but...
Right. Like, it is small. Like, if the largest one I think they found was like 50 kilograms. It's heavy, but it's still compared to
that's a headache.
Else, it's pretty small.
If it hits you, yeah. I mean, literally any of these would kill you if you're on the moon.
Right. So, you look at how do we actually get to the moon? How do we live on the moon? A lot of the research now has been done. Can you go into these old lava tubes on the moon, kind of camp out underground? They're not really worried about these little tiny meteorites. Like, it'd probably be pretty rare, more so for solar flares or any kind of cosmic ray events. But yeah, it would help you out from these asteroids as well.
Yeah, and so I mean, does it tell us as well just about the state of, like, how much debris is left in the solar system? I mean, we think about these periods, like back in the beginning, there was the late heavy bombardment and there was all of these enormous asteroids circling around, but like, how much is still out there?
That's a good question. To be honest, I don't really know the answer to that.
Yeah.
I know a lot of this they are looking for kind of spontaneous hits, not ones that are from like the Perseid or Gemini meteor showers that we know about. So I guess it does kind of give you a handle on for what is there outside of these meteor showers. That'll be my
guess. I mean, you think about things like how astronomers, they've seen a lot of the meteorites that have landed here on Earth. They've been able to actually trace them back to specific asteroid groups, and in some cases there are whole asteroid groups. There was like one large object that was smashed up into smaller pieces, and those pieces are roaming around the solar system, and we know that because some of them are here on Earth, and they're all related, and you can actually trace them right back to the home asteroid. But I guess, you know, there's only so much you can tell by watching something, you know, light on fire on the moon. That's awesome. Thanks, Michael. Brian, we got one more story from you.
Yep. So before, I would add one other thing. With the things landing on the moon, they would give you the distribution of sizes, because all of these would burn up in the atmosphere, so we wouldn't be able to study them here on Earth. But by hitting the moon, you can say, okay, is the distribution of sizes, does it follow the same scale that we think and what we see with larger asteroids?
So for every, right, okay, so you've got like we know the bigger end of the scale. We know how many ones that are 100 meters across, and how many are 10 meters across, and how many are a kilometer across.
Right.
And we know this bell curve, this distribution curve across them, but now we can look at the small side and then assume that there's a connection in between from one to the other.
Exactly.
Yeah, that's really interesting.
I think the goal of the study is also
interplanetary missions, satellites, things like that. This is an important set of data to know.
Yeah.
Yeah, they're looking at like decimeter to meter size, so like, you know, about this big to like this.
Right.
This big. So yeah, it's relatively small.
Yeah, and it tells you like how much you might need to harden your spacecraft to whatever size of debris you might expect out there as you leave the Earth's protective regions. Yeah. Yeah. Interesting.
Yeah. Softball-sized rock can definitely damage your spaceship.
All right. So Brian, cosmology is totally wrong, and we need to re-understand the universe.
Yes, exactly. No. This is a really kind of interesting thing. There's been a couple of studies like this, and you want to take it cautiously. So one of the fundamental things in physics is that, you know, when we look out into the universe, the behavior that we see is governed by the same laws of physics out there as it is here. And so the speed of light is the same everywhere. The way space and time work is the same everywhere. This idea is kind of fundamental to being able to do astrophysics. That we have to be able to connect what we see here on Earth with what we see out there. So one of these fundamental assumptions is that the universe is isotropic. And what that means is, on a large scale, not counting clustering of galaxies and stuff, but on a large scale, no matter what direction you look in the universe, what you're going to see is going to be basically the same. Right.
Because we're not special.
Right. We're not special. And so one of the things in general relativity is, if the universe is expanding because of a cosmological constant, kind of a structure of space and time, in relativity, that constant is a constant. And so that means that the universe should be expanding at the same rate no matter what direction we look.
Right.
So this is kind of basic physics that we've had for nearly a century now. So you still want to test this idea. And we've had lots of studies that look at the expansion of the universe, and it does look to follow consistent expansion in all directions. But we have a study like this that hints that maybe it's not quite as clear as we think. So what this new study did is, you know, we typically measure expansion by looking at things like supernovae or the cosmic microwave background. And those both give you kind of a uniform direction. What this team did is they looked at X-rays from galactic clusters. So in clusters of X-rays, there's intergalactic gas, and it can get heated to the point where it gives off X-rays. Now, the nice thing about this is that when you look at the X-rays coming off of this hot gas, it has a specific spectrum, and you can tell what its temperature is by looking at its spectrum. So it's kind of like a black body radiation. If you look at the distribution of light, you can tell where the brightness, you know, what its temperature is. Well, if you know its temperature and you know the gas there, you know how bright it actually is. And so then you can compare it to how bright it looks to us. And that depends upon how far away it is. So what you can do is you can use those calibrations to measure the rate of expansion between us and these distant superclusters. So they did this for hundreds of superclusters. And what they found was the expansion rate was not the same in all directions. What they found was what they call a dipole, which means on one side of the universe, it's expanding slightly slower than on the other side of the universe.
Which means that maybe we are special.
Well, you could say maybe it means that we're special.
Maybe we're the center of the universe, man.
Well,
or actually, maybe there is a place that's the center of the universe. Yeah, but it's not here.
No,
someone's right. So at least
so there's a couple of things that could do this. One could be that we know that there's a lot of evidence that the universe exists beyond what we can see. So the observable universe is only a portion of what the actual universe is. So if there were a super mega cluster outside of the observable universe in one direction, that would cause the expansion to look larger in that direction than it actually is, because it's like the great attractor,
right?
Where part of the universe is going in that direction because there's some super duper cluster outside of the observable universe. So that's one thing that it could be. Another thing that it could be is that the universe really isn't expanding at a uniform rate, that dark energy is somehow not evenly distributed. So there'd be more dark energy in this region of the universe, causing it to expand more, and less in another region. Of course, there's a third possibility, which is they have calibration errors in their data.
Right.
Because they have to build all of these into the model. And if they have some kind of systematic bias in the way they're observing it, that would throw off the data.
Allow me to propose what could be the cause. Dust. It's always dust.
So dust is one of those things that you could look at. It's with the spectrum, you can generally tell whether there's dust there.
That just means that it's dust you haven't figured out yet, because it's always
you can
dust.
always say there's something in between, or it could be it's dark matter that's absorbing X-rays in different ways. There's ways to kind of continually go down more exotic models, but when you look at the overall data, what you get is something that is tantalizing but not conclusive.
Right.
And so you have this data that kind of hovers on enough to be suspicious, but the amount of confirmation data you would need to prove that we are wrong about the universe is huge, and this doesn't meet that bar.
Right. And that is one of the bedrock foundation of this entire science is that wherever you go around the universe, you should roughly see the same thing.
Right.
And if you can't, then it's very difficult to make any predictions at all about the universe beyond a certain scale if you can't make that basic underlying assumption. And up until this point, It has always held up. And so for it to not hold up would be pretty weird.
Excuse me. Right. So this would not throw out basic physics on Earth. This is not, even if this is absolutely proven, it's not going to throw that out. But what it would do is it would force us to revise our cosmological models.
Mm-hmm.
Because the foundation of our models is based upon isotropy. So we could tweak it on cosmic scales and come up with new models. But our current models don't assume that.
So, let's say that other astronomers come along and they do really super detailed observations and they confirm that this is true. Are we in Nobel Prize territory?
I think if you had enough conclusive evidence that you could be, it would certainly change cosmology. The thing is, we have these studies every now and then that they kind of hint at this. But then we have other studies that don't. So one of the things that's puzzling about this one is that the signal level for this variance is strong enough it should show up in the cosmic microwave background. So if we look at the cosmic microwave background, we should see a similar dipole moment, and we don't.
Right. There is the weird spot, the cold spot, but apart from that,
right, there are cold spot things, but we're not seeing an overall dipole moment that's not due to just the galactic motion.
Right. That if you look one way, the universe is expanding faster away than if you look the other way. And that's pretty strange. So
and we don't see that in supernovas, and we don't see that in the cosmic microwave background. Both of those show a uniform distribution.
Yeah. I mean, do you find like right now cosmologists are pretty stoked by just all of this stuff that's happening? I mean, it seems like it's a really exciting time in cosmology.
It's a very confusing time in some sense. I mean, all of our assumptions, like when I was in graduate school, we had like 5 different models and any one of them could be right. And then we kind of threw all of them out, but we got the right model, we thought. And now we're back to this model doesn't quite work.
Yeah. I mean, Michael, you're a lot closer to it, right? I mean, are you finding that your professors are giving you the standard model, or are you getting a chance to sort of explore some of these alternatives now?
When it comes to classes, it's all standard model. And, colloquium discussions, and they can bring up the... kind of a short story is when I was visiting Penn State, that was when Planck just came out with its results that revised the Hubble constant. And one of the professors is kind of screaming down the hallways, they messed up H0, they screwed up the age of the universe. So in the hallways, you can get these kinds of conversations.
Right. But in terms of the actual classes, it's good old 13.8 billion years old for your universe.
Yeah.
And it's expanding in the same speed in all directions.
When I was teaching, I would bring up these kind of side things, and you'd see the students writing really fast, and I'd say, and so this is an interesting thing that could lead to this and this, but none of this is going to be on the exam. It's like, put their pencils down.
That's awesome. Yeah. All right. Well, Brian, you're on my screen right now. Tell us what you're working on and where people can find out more.
I'm currently working on stuff for NRAO for the next day or so. So that's my other
So it's a
quote unquote real job, and then I'll go back to popular science articles. But when they show up, you can find them on briancoberline.com. You can find them on Universe Today.
Yeah, I like that website.
And you can find me on Twitter at Brian Coberline.
Right on. Beth.
We are working on launching a Facebook group for science artists under the SETI Institute flag. We just opened it up today, so if anybody has any interest, at me on Twitter.
Explain more. That's cool. So what are you looking for?
We're just looking for visual artists of any sort of type. Actually, I'll take anything written too. We will be giving monthly challenges. We're announcing the first one tomorrow. And then basically we just want people to play in our science and have a good time. That's cool. Give artists some place to kind of share all of those things with each other. So it's at SETI Institute on Facebook and Twitter. So if you want in, let me know. I'm sending out invites.
That's fantastic. I mean, as a person who relies heavily on the space art that is released by various groups, we see the same pictures again and again and again. So if anyone wants to take a crack, because there's so much interesting stuff happening, if there could be more artwork out there that we could help, to go along with our words, that would be wonderful.
Yeah, and I based it off of, I've been running a hashtag SciArt Sunday on Twitter via the SETI Institute account for about a year now, and it's gained a lot of traction. So we thought we would kind of play off of that and keep moving on with some of these artists. Awesome. and get more work and see what they can do.
That's great. Michael, what are you working on?
Right now, it's kind of just research, trying to get my paper and PhD up. I've also, as mentioned, I got a foster dog. She's down here, little black pile there. So I'll be posting photos on my Twitter account at Michael Roderick, and you can
have you
foster dog.
Have you had a conversation with her that this isn't normal, that she shouldn't expect this kind of access to you forever in the future?
Yeah, she's like my shadow right now. She is firmly attached. It's
Yeah.
gonna be hard when when we part.
It's funny. We rescued a dog as well, like maybe a year and a half ago, and I think for like the first time that we've had her, she went off to a different part of the house and laid down and just like did her own thing. Like for the first time, she's like, okay, this dog is finally feeling like the rug won't get pulled out from under her the first second, she stops being in constant vigilance, which I thought was great. And so where can people find out more about your work and your dog?
So I'm on Twitter at Michael Roderick.
Awesome. All right. And of course, we've been working on a lot of still great stories over on Universe Today. We had a fun interview with Dr. Ryan Watkins earlier this week on my YouTube channel. So I've been interviewing many. I keep making the joke every week. Everybody's trapped at home and they all know how to use Zoom. So I am interviewing. It's just a feeding frenzy, and I am interviewing everybody. So definitely come by and hang out for some of our live streams over on my YouTube channel. All right, I'm going to put everybody back on the screen. As always, it is a pleasure to hang out with all of you and explain the space news of the week. Thanks to all of our moderators. Thanks to everyone watching us this week, both on YouTube and on Twitch. We know you're there. We really appreciate all of your help. Special thanks, as always, to Nancy Graziano and the rest of the Weekly Space Hangout crew for helping to keep us organized week after week after week. We could not, literally, would not do this show without them. I'm telling you right now, if they didn't exist, I don't want any part of this. They're awesome. So, thanks everybody, and we will see all of you next week.
Okay.
Bye.
Bye.
Bye.